Last time we saw pseudo-random generators and how to create a pseudo one-time pad, which used a pseudo-random generator to create to encrypt messages where technically the uniform key is much smaller than your complete message, right? Here's how the pseudo one-time pad looked. Pseudo one-time pad, right? Here was the idea. The G be a deterministic problem, deterministic algorithm, deterministic algorithm with G of k is equal to P of k, some polynomial in the length of k. How did generator work? Generator given input 1 to the n outputs a string, outputs output a uniform key n bit key. Okay. Now, what did we do with this n bit key? Well, the length of the n bit key, which is n, is our security parameter. Security parameter is equal to n. Okay. What did encryption do? Takes input key k belonging to 0, 1 to the n, and message m in 0, 1 to the, well, what do we want? We don't want it in n, we want it in p of n, right? In p of n, and outputs ciphertext c, which is equal to G of k XOR summed with m. What did decryption do? The exact opposite. Takes input as key k belonging to 0, 1 to the n, and the ciphertext, which is again c of length 0, 1 to the pn, and outputs message, which is m, which was equal to G of k XOR sum m, right? Once again, the correctness was obvious, and the goal now was to show that is this secure. Goal: show pseudo OTP one-time pad is computationally secure up to some assumptions. The most important of which is that G is a pseudo-random generator, right? i.e., G is a pseudo-random generator. We don't even know if pseudo-random generators actually exist, right? We talked about that last time. We said that we don't know if the algorithms we currently have are actually pseudo-random generators or not, but we assume that to be true, that they are pseudo-random generators, and we just hope that that works. Okay? And so based on that, today we are going to show that um, this uh, pseudo OTP is then what do you call, then computationally secure. Okay, and the way we prove it is by a process called reduction. So proof by reduction. Proof by reduction. Okay, there are various methods of doing this. One of the methods that is standardly used, usually used, is using NP hard problems. NP hard problems. Okay, so NP hard problems are some really hard problems that we know, well, that we assume are not doable in polynomial time by any efficient algorithm. Sorry, a polynomial time algorithm cannot solve these problems. Okay, with higher than a higher than negligible probability. Okay, so if you don't know that, if you don't know what all of this is, that's fine. But here's how we are going to use this. I will show methods which don't rely on it, and that is what we'll be using. But for now, let us assume this is how we are going to do it. So fix efficient algorithm, efficient adversary A, adversary A prime, A attacking P, attacking pi. My encryption system, which is pi, is being attacked by A. Okay. Denote its success by probability epsilon with success probability epsilon n with success probability epsilon n. Okay. Then in step 2, we construct an efficient algorithm A prime, which uses A as a subroutine to solve some problem, which uses A as subroutine to solve problem X. Okay, so X is going to be a NP hard problem that A prime is going to solve. Okay, and how is it going to solve? It has no idea how A works. Okay, A is going to attack pi. Okay, and this is how it's going to work. A interacts only with pi. Only with pi. Okay. And B, so A prime, even though it is running A only interacts with pi, and A prime succeeds when A succeeds with pi. So if A succeeds in breaking pi, then that should allows A prime to somehow solve X. That allows A prime to solve X with some inverse polynomial probability, with some probability bi probability 1 over P of n. Okay. Now note 1 over P of n is not negligible. Okay. However, even if 1 over P of n is not negligible, A prime then solves problem X with probability A prime solves X with probability epsilon n over P of n, epsilon n over P of n, which is negligible if epsilon is negligible, and it is not negligible if epsilon is not negligible. So it depends on epsilon being negligible or not. It behaves the same way as not. So if epsilon is not negligible, this entire probability is not negligible, which would contradict initial assumption that X is a NP hard problem. So given our assumption regarding X, we conclude that no efficient adversary A can succeed in breaking pi in breaking pi with a non-negligible probability. Okay, that is one approach which uses a different problem X that we are attacking. Okay, another approach is to attack the pseudorandom generator itself. We assume that we are dealing with a pseudorandom generator, and we set up a code such that if this algorithm was failing, then we could attack the pseudorandom generator with non-trivial probability, and the algorithm can distinguish whether the string is given by a pseudorandom generator or a normal generator. Okay, so second approach, one, assume G is a pseudorandom generator. Why? Pseudorandom generator. Second, assume contradiction, that there is an attacker who breaks the OTP scheme. Assume contradiction, that there is an efficient attacker. There is efficient attacker A who breaks the scheme, who breaks pseudo OPT, pseudo OTP. Okay, and use that. Use A as subroutine to build efficient D that breaks pseudo randomness of G. So rather than attacking with a different problem, which is NP hard, we can just attack the pseudo random generator, which we are assuming it exists. Okay. And so by assumption, since we have assumed that it's a pseudo random generator, by assumption no such D exists, no such D exists, which is to say, so for no such A exists, no such A exists. Okay, that's another way. Or alternately, it's just modifying this method. 3. 1. Assume pseudo random generator. Assume G is a pseudo random generator, PRG. So this method is a combination of both of these, both of the previous methods. Okay. Second, fixed arbitrary efficient A attacking OTP scheme, pseudo OTP. Fix arbitrary efficient A attacking pseudo OTP scheme. Okay. Then we use this to build an attacking. We again use this to build a D which attacks G, but as a subroutine. Use A as subroutine to build efficient D attacking G. And now here's where we are doing it the same way as method 1. We relate the probability of D to success of A. Relate probability of success of D relate distinguishing probability probability D of D to the success rate of A, to success probability of A, probability of A, hopefully by inverse polynomial, by some 1 over Pn. Okay, so once we have that, by assumption the distinguishable probability of D must be negligible by, okay, so we don't even need it to be actually this. So by assumption do I need it to be, I need it to be at most polynomial. Yeah, oh, I think it's fine. By assumption the distinguishing probability of D must be negligible, of D must be negligible, because we have assumed it to be a pseudo random generator, which allows me to bind the success probability of A. This bound success probability of A. Okay, so if you get it properly, you can bind the success probability of A and show that, oh, A cannot succeed at more than a certain probability. Okay, so it is negligible. It succeeds with negligible probability. And this is the idea we are going to be using to prove theorem 3.18 in the book. So theorem 3.18. If G is a pseudo-random generator, if G is a pseudo-random generator, then the pseudo OTP, then the pseudo OTP as generated, as described before, as described before, is a fixed length private key encryption, is a fixed length private key encryption which is EAV secure. The is EAV secure. EAV secure. That is to say, computationally indistinguishable. Right? Computationally indistinguishable. Okay. So, how do we do this? Proof. So let A be an arbitrary advisor. Let A be an attacker. Okay. So let A be PPT adversary. PPT adversary. Okay. And D be a distinguisher. D distinguisher, which we will construct as follows. Constructed as below. How do we construct? D is given an input. D takes input. D takes input W, which is a string 0, 1 to the length Pn. Okay. That we have from the pseudo-random generator of if n goes to Pn, then this is going to be Pn. Okay. Then first run A of 1 to the n to obtain messages m0, m1 belonging to 0, 1 to the Pn. So these are Pn length messages that the adversary pops out. An adversary in a standard EAV test, if you remember, gives out two messages that we need to check. Choose uniform bit B 0, 1, set C is equal to W XOR MB. 3, give C to A and obtain output B prime. Obtain B prime. Output 1 if B is equal to B prime and 0 otherwise. And output 0 otherwise. Okay. So the role of G is to figure out whether the role of D is to figure out whether a string is actually pseudo-random or not. Okay, so D clearly runs in polynomial time. Okay, so that's my first step. Okay, modify pi uh, so modify pi is equal to pi tilde, and modify pi to pi tilde is equal to generator encryption decryption. Ooh, I forgot to mention that pi is actually a one-time pad. Okay, pi is OTP of length what do you call PN? Okay, so it's a proper OTP, not a pseudo OTP, and we are taking pi tilde to be the pseudo OTP, to be the pseudo one-time pad. Okay, so pseudo one-time pad we have discussed before. That is what we have. Okay, now did I mess up? Did I want to say the other way around? Ah, yes, my bad. I messed up. To be, this is the other way around. This is actual OTP to be a real OTP, real OTP of length. What is the length? PN. Okay, so what it does is it takes the generator takes, i.e., given input 1 to the n to gen tilde, it produces a uniform key which is of length uniform key, okay, of length 0 1 to Pn, and uses this to encrypt message. Okay, so rather than throwing it via pseudo OTP, this is more or less a proper OTP. Okay, in that case, perfect secrecy of the one-time pad, perfect secrecy of one-time pad implies that whatever I do, whatever my algorithm does, this is going to be pi tilde of n is equal to 1 is equal to 1/2. Right? Now, to analyze how D works, we look at a certain things. To analyze behavior of D, analyze NALYZE behavior of D. Note that if W is uniformly chosen, W is uniformly chosen from 0, 1 to Pn, right? Then this is running a proper one-time pad. If W is chosen from 0, 1 to the Pn, this is just a proper one-time pad running on length Pn subroutine. Therefore, then then A running this experiment, running in the subroutine, is identical to privet A pi tilde n. Okay. Therefore, probability that W is chosen from 0, 1 to the Pn uniformly, and then D succeeds, D of W is equal to 1, is the same as probability that the private key inscription of A pi tilde of n is equal to 1, which is equal to 1/2. Right? So on the other hand, if we run if W is chosen from uniform key from k belonging to 0, 1 to the n, and letting W is equal to G of k, right? Then this is the same as the experiment being conducted on a one-time pad of length of everything of length n, right? Then this is same as a running a succeeding in prove a pi prove a pi. Okay. Therefore, the probability of success of W if you're chosen from 0, 1 to the n, and then, sorry, not W, K being chosen from 0, 1 to the n, and then you take the distribution here and ask whether your experiment succeeds, is the same as the probability that the experiment succeeds on a pi of n is equal to 1. Right? However, we have assumed that G is a pseudo-random generator, right? We assumed G is a pseudo-random generator and that D runs in polynomial time. So the probability of the success between these two is going to be negligible. So there is some negligible function epsilon of n such that where is it? Probability of W being chosen from 0, 1 to the Pn dW is equal to 1 minus probability that K is chosen from 0, 1 to the n fed to the pseudo-random generator Gk is equal to 1 is smaller than or equal to epsilon n, right? That is what it means for something to be a pseudo-random generator. This probability should be negligible. Therefore, we get that 1/2 minus the probability that the private key encryption of a pi, which is the scheme with the pseudo-random generator, that this experiment succeeds is smaller than or equal to epsilon n, which implies the probability of private key encryption a pi of n is equal to 1 succeeds with probability smaller than or equal to 1/2 plus epsilon of n. Okay. And thus, I have shown that if A was an arbitrary PPT, thus any A arbitrary polynomial time PPT adversary polynomial probability time adversary thus can only succeed with probability negligibly more than half, implying that my system is secure. Therefore, sudo OTP is computationally secure. Computationally secure as required. Okay. So we showed that this is computationally secure, and this is great, but still there is some caveats. There are some um, points that need to be mentioned. We have not proved. We have not proved that sudo OTP is secure. Sudo OTP is computationally secure. So I'm going to drop computationally because most of the times whenever we say secure, we will mean computationally now. Unconditionally. We have not proved that secure unconditionally. Okay. It relies on a very big assumption that G is actually a pseudo-random generation. Relies on heavy assumption that G is a pseudo-random generation. G is a pseudo-random generator. Okay. And it also relies that our definition of secure is strong. And on our definition of secure, so relies on a heavy assumption that G is a pseudo-random generator, and on our definition of secure. Okay, so that means the only way, therefore, the only way the scheme can be broken, this scheme can be broken, and I'm not saying broken as in, oh, I accidentally managed to break it with probability 1 over 20 to the 2 to the minus 200. No, actually broken where I can show that I'm succeeding with more than negligible probability is if there's a weakness in G, weakness found in G, or if the definition is not sufficiently strong. If the definition is not sufficiently strong. Okay. So what does that mean? What do we mean by not sufficiently strong? We will see what it means by not sufficiently strong. Okay, I will get to it since we have time. But what have we gained so far before moving to stronger definitions? What did we get? What have we gained? What did we gain by pseudo OTP? Okay. Did we gain anything? Okay. So the first biggest thing we gained is that the pseudo OTP has a shorter key than the message. Shorter key than the message. Key than message. Okay. We had seen a theorem in chapter 2 that said that, oh, you can never have a key space which is smaller than your message space. Then your system is never ever going to be secure. And yeah, we could not break that. We lost, managed to reduce size of key space for negligible loss of security, loss of secrecy, right? So we went from perfectly secret to computationally secret, and for that, the probability we are saying of success is still really low, but we have a much smaller key space. We are much more independent on what to do, and the fact that this allows the parties can internally generate temporary uh, temporary n bit strings is mostly irrelevant. Bit strings to encrypt / decrypt is irrelevant. Okay, as great as that sounds, oh, I have to create n-bit strings. The small problem is that we still need to share the key in advance. Okay, key still needs to be shared in advance. However, in real world, this means you don't have to store the entire big key. You can store a small key. In real world, you don't need to store. You can avoid having to store pn-bit keys. Okay, since they're temporary, you don't need to have them. Okay, so this is what we gained from using OTPs. Okay, now pseudo OTPs. Now let us recall something. Perfect secrecy has two limitations. Perfect secrecy has two limitations. Okay. First, key length as long as message. Key length as long as message, which we are solving right now, right? Pseudo OTPs allow us to circumvent the first one, and the second one was key can be only used once. Key can only be used once. Okay, so pseudo OTPs circumvent first issue, first limitation. However, the second one is still the same. Second limitation still exists, right? So the question becomes, how do we circumvent that? Is there a way to question? How do we circumvent the second? How we circumvent the second one? Okay. But the problem is, if we do want to circumvent, we need to define what it means, first of all, to be secure for these things, right? As of now, our definition of security only relies on one message. Being able to say with probability, if we are sent one message, is this M1 or M0, should be half or close to half, is what our definition of probability means, as of our secrecy definition of secrecy means. So first, we need an appropriate definition. To answer this, we need an appropriate security definition first. Okay. Which means we need two things. First, a security goal. And second, a threat model. What are we trying to keep security safe under? Okay. So we are going to keep the security goal the same. We will keep goal same while strengthening model. Okay. So our single message secrecy so far that we defined was as follows. You had a user 1, which I'll call U1, who sends a message with a ciphertext to U2, and this ciphertext can be intercepted by adversary A, right? And the goal was he takes a key K and defines C is equal to encryption K of M. And the goal was the adversary A should not be able to figure out from the ciphertext C what the message M was, right? With negligible success. Now we want a slightly better model. We want to say, oh, again, U1 is still sending message to U2. And it's still being encrypted by some key K. However, this time, instead of just one message, the adversary can see multiple messages encrypted by the same key, CT. M1 ... MT, and we want that C1 should be encrypted M1 ... CT encrypted K MT, right? If we can somehow so M is equal to decryption K C and CI MI is equal to decryption K of CI. The model remains the same. The idea of what we mean by secure still remains the same. The success probability should be about close to 1/2 is what we want to desire, what we desire. And we want to say that for all of these messages, even if he does that, even if he sees all these ciphertexts at the same time, that still shouldn't give them much better idea. Okay, so definition. Fix pi and a. We know how pi and a works. No, a should be fancy as before. And now define a randomized experiment. Define a randomized experiment. Experiment priv. Now this one will be multiple of a comma pi of n in the following way. First, a outputs vectors, two vectors m01, sorry, m01, m02 dot 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 m0t, and m11, m12 dot 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 m1t. So they're both length t vectors. Okay, so they're all messages. Now we are not saying that ideally we are not saying that both of these every single message should have the same length, but at least this much should be true, that the length of the message m0i should be the same as the message length m1i for every I. Okay, in the second step, well, generate a key k from generator 1 to the n, take a random bit 0 1 for every I, so that ci is encrypted by k to mbi. So actually we are going to assume that this is the same for every, so the length of m1i is equal to k, is equal to n. Okay, so we are saying that all the messages should be of length n, so we don't have to worry about that. We'll assume that everything is of length n. B prime is generated by a after seeing his messages c1 dot 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 ct, and we say a succeeds, c succeeds if b is equal to b prime and experiment fails, experiment evaluates to 1 in this case. Okay, and we say that the we say pi is multiple message indistinguishable, multiple message indistinguishable, multiple message indistinguishable if for all PPT attacks, if all polynomial times probability, what was PPT again? Oh, whatever. PPT attackers A, there's a negligible function epsilon there is a negligible multiple message distinguish negligible function epsilon such that private key the probability of success of private key under a multiple encryption API of n is equal to 1, as in the experiment succeeding, is smaller than or equal to 1/2 plus epsilon over n. Okay. Now, here's the first problem we face. Okay. Note OTP is not multiple message indistinguishable. Okay, so first big problem, OTP or pseudo OTP is not multiple message indistinguishable. Okay, in fact, no deterministic stateless encryption scheme is multiple message indistinguishable. Scheme is multiple message indistinguishable. What does this exactly mean? We'll get to that later. What it exactly means by stateless encryption. Okay, but we know what non-deterministic is. If you encrypt the same message using the same key, it should always give the same exact answer. And that should, in a way, give you a hint of why this doesn't work. If you look back at our definition here, it says you can choose two columns of vectors, right? What happens if I take M11 to be M01 equals M02 and M11 not equal to M12? You're going to get some some ciphertext, right? If you're using the same key, if your first two are the same, then there is a heavy chance that M11 is equal to M2, that the message encrypted was M01, right? Because if C1 is equal to C2, using the same key, M1 better be equal to M2. That means it's M01, M02. If M1 and M2 were different, they should have been encrypted to do different things. That's why no deterministic stateless encryption scheme can ever be multiple message indistinguishable, right? So is this really what we want? So generally we are not going to be working with so note ends here. We will not be working with multiple message secrecy. We will not work with multiple message secrecy. Instead, we will work on define something stronger. Instead, we will define something stronger. Which is security against chosen plain text attack. against chosen plain text attack, which is generally denoted CPA security. Okay, and this is nowadays the minimal standard of encryption that is expected. Okay, so we will look at this next time. What was chosen plain text? You're allowed to send a message with a chosen plain text once, and then you have to get the next message. Okay, but we'll look at that in the next lecture. For now, let's stop here.